Hello, everyone. So we want to welcome you to the next chapter in the Deep Learning book. So we're going to be actually covering chapter 4 today on numerical computation. And my awesome co-host here, Safak, is going to be giving us a presentation. And I will be sharing a link as well to his slideshow presentation for you guys. And then we'll be pasting it as well in the meetup group for you. So you have a reference to it, which is great. Safak, do you want to go ahead and introduce yourself?
Yes, my name is Shafak. There's an invisible H in my first name, and I have a background in computational engineering and numerical models and computational fluid dynamics. Right now, I am looking for full-time data science positions, but in the meantime, I'm also working on contract jobs. And today, I'm going to present you the 4th chapter from Ian Goodfellow's Deep Learning book.
Thank you. So I'll actually give a quick little intro to how the flow of this goes really quickly before we get started. So for new people that are joining us, what we're doing is reviewing the Deep Learning book by Ian Goodfellow. And so what we do is we have someone actually sign up to present on a specific chapter each week, and every 2 weeks. And so they go through the chapter and we'll put together a little presentation for us. And it can be as short, we say as like 10 minutes and as long as an hour or two. Our last one was about 2 hours. It could have gone longer. Some of the later chapters are actually very dense. And so potentially we might be splitting those up into more than one person, more than one presentation. But for now, we're sticking to one person per presentation. And if you're on our meetup page, you can actually go to the Excel spreadsheet to sign up to present on either the online sessions, or we're also hosting these in person in San Francisco on every other Monday as well. And I'll go through that again at the end of this, but I think we're probably ready to start if you want to go ahead, Shafak.
Okay. So this chapter talks about the numerical computation aspects of deep learning and the gradient descent algorithm. It starts off with the rounding errors concept in numerical mathematical models. So one key concern of software engineers have, especially those who develop the low-level libraries like NumPy and Python and whatnot. But for like programmers like us, we don't really need to worry about the underflow and overflow and rounding error issues too much. But it's good to know how it happens. In deep learning, we encounter the softmax function pretty often. We encounter it in categorical distribution for multiple categories, like in image classification and whatnot. And softmax function is basically it exponentiates the scores of n many categories. And if the scores are, for instance, if the scores are all the same, it's equal to a constant c. But if the constant is a very large but negative number, raising it to the power of e will make it a very, very large negative number. And if it's going to be a very small number. I'm sorry. It's going to be a number that's going to be very close to 0. And the computer has only 16 digits if you're using double precision. And you might have the risk of running it off to 0. And if the denominator is it comes out as 0, it's going to throw you an error. It's going to be equal to an infinity, basically. So the exponentiation can underflow when the argument is a large negative number, or it can also overflow when it's a large positive number. Here I have a little bit of code. So I set two variables, one to a very large constant number, like a billion, 10 to the power 9, and I'm gonna add a very small number, which is epsilon 10 to the minus 6, a millionth basically. I'm gonna add this for 1,000,000 times. Analytically we know that if you add a million times to a constant number, you're just gonna raise it by 1. But on Python, if you run this on the IPython shell, you will see that you're not going to get exactly 1, because all these rounding errors at each iteration of this like million iterations, it's going to add up cumulatively, and it's going to give you like a 5% error here. And this is let me see, on the right hand side I have this. Let me see what I've done. So I am adding this epsilon 1,000,000 times, and then I'm subtracting the same number. So the rounding errors are actually canceling each other out on the right hand side, but on the left hand side you will have this rounding error accumulation error. So it's good to know that this is a possibility in numerical computation. And this is a concept. Condition number is a concept that I really enjoyed learning about. The condition number of a matrix is defined by the relative error in the matrix equation AX equals B, the ratio of the relative error in X to the relative error in the right-hand side vector B. This condition number is important for a number of things, in particular in inverting a matrix. If the condition number is very large, then the rounding errors will accumulate, and the inverse of the coefficient matrix A will be inaccurate. And last night I went through all the derivation, but I'm not gonna go through that step by step. The worst case, so the kappa A, the condition number, comes out to be the ratio of the maximum to the minimum eigenvalues. And the worst case happens in this error transfer from right-hand side to the unknown vector. Happens when the epsilon, a small inaccuracy, small perturbation to the right-hand side vector B, if epsilon is aligned with the minimum eigenvalue eigenvector, the eigenvector that corresponds to the minimum eigenvalue, then that small perturbation to the right-hand side vector is going to propagate to the unknown vector, to the left-hand side of the equation, greatly. And the ratio is like exactly given by the condition number, the ratio of the eigenvalues.
Hey, Shafak, do you
Yes.
mind describing an eigenvalue just for people that are joining us for the first time, might not be familiar with it?
Eigenvalue is a very important concept for linear transformations, for linear equations. Here I have AX equals B, and the characteristic equation, so-called the characteristic equation or the eigenvalue equation, is given by AV equals lambda V, where V is the eigenvector of A, and lambda is the eigenvalue of that corresponds to that particular eigenvector V. And A, if the matrix A is n by n matrix, it basically describes a system of linear equations, n linear equations in n unknowns. And in such a system, you will have n many eigenvalues and corresponding eigenvectors. And these eigenvectors are very special vectors. They designate a very special direction on which this linear transformation, the matrix A, when this linear matrix A acts on that any vector that aligns in that direction, in the eigenvector direction, that the result of the linear transformation will be in the same direction of the initial input vector. So there's no rotation there at all. So for real and numbered and symmetric matrix, all these eigenvectors will be orthogonal to each other. I don't want to go too deep into eigenvalue and eigenvector concept. I think we already covered that topic in the previous chapter, I believe.
Yes, definitely. I just wanted people who are new to get a quick overview, but that's perfect. Thank you very much. Yeah.
Okay.
Yeah.
So if eigenvalues, if the minimum eigenvalue is very small compared to the maximum eigenvalue, then you're going to run into some problems, slew of problems, especially in numerical modeling, because no number on the computer will be described as its full extent. You know, like pi will be only described by 16 digits, but pi is just an irrational number. It goes for infinity, so it's going to be just an approximation, a 16-digit approximation of the real value. And so the condition number is it gives you a very good measure of how much round of errors you should expect. The next slide, let me get a sip of water.
Mm-hmm.
So I'm gonna tie this to our machine learning problems.
Awesome.
In machine learning, we always have a loss function. It's either a hinge loss in an SVM model or a softmax, or yeah, softmax loss in multinomial distribution problems. And so in machine learning problems, we are not solving for f of x equals 0. It's not a root finding problem. We're minimizing the loss function. And you know, we have a data matrix M, and M is usually, you know, typically it's a M by N matrix where M is much larger than N. And typically, you know, in image, you know, recognition problems, for instance, where N could be, I don't know, 1,000 features, but N will be many more multiples of number of features you have. And so the data matrix itself will not have eigenvalues because it's not a square matrix. It's not going to be described as an AX equals B format system of equations. But one concern we have might be multicollinearity, for instance. You know, in your features, would you like to be sure that all the features are linearly independent from one another? You have to look at the eigenvalues of the correlation matrix, which I put in here as NT dotted into M, the data matrix. So this is feature-feature correlation. It's going to give you the feature-feature correlation matrix. It's going to be a real numbered and symmetric matrix A. And it's going to be a square matrix. And if the minimum eigenvalue, or rather, if you have 0 eigenvalues, for instance, then this is clearly going to show you that you will have at least one feature that is not independent from the rest of your features. And in machine learning, we try to be economical in the features we use for several reasons. Some of them is to make the computation easy. So we try to find latent features and eliminate features that give you the same information. And the conditioning number here can be used to see if your features are whether they're independent or linearly independent of one another or not. If the condition number is 0, that clearly shows you have at least one feature that is not independent from the rest of your feature set. But if it's a large number, that means the minimum eigenvalue is much smaller than your maximum eigenvalue. So it's still not a very good thing, because it means several of your features, at least one or more, are giving you very little information that the rest of the features hasn't. And here's some terminology. If your conditioning number is in the order of 1, it's well-conditioned. If it's a very large value, it's ill-conditioned. Let's say if your condition number is about 10 to the 9, then rule of thumb is you will lose 9 digits of accuracy in your computations. The next slide. Let me see if I have something here that I haven't already talked about. I think I have covered this. M is your, in a typical machine learning problem, M is your data matrix. And yeah, the data matrix, and you are trying to find a optimum solution to mx equals y, because there's no exact solution, since the solution space is multidimensional, basically m minus n dimensional, if all your features are linearly independent. So yeah, this is a typical like a least squares like problem that I was trying to put on the slide. So since you can't solve for mx equals y, you dot both sides of the equation with m transpose, and you get a least square solutions this way. And in that least square solution, you have a coefficient matrix A, and you can look into the condition number of A. But I covered this already in the previous slides. Next slide. The chapter, so the book goes into talking about optimization and gradient-based optimization and gradient descent from this point on.
Can you give us an example of how optimization is used in machine learning?
An example. So, again, in machine learning, a typical problem can be boiled down to an underdetermined set of equations, mx equals y, where the solution space is, it's multidimensional. So you're trying to find the best solution that minimizes an error, a loss function. So you can't solve exactly for y. So here you're solving for m transpose y. So that's the best you can do with the data set you have, because you're trying to learn from data in machine learning. Typical problem would be, what's the typical problem in machine learning classes that they introduce in first few?
Usually, linear regression is probably the most well-known, right?
Yeah, linear regression. Like, assume you have 2 features to predict real estate house property values on the market. And it could be based on several things like location, size, how many bedrooms it has, and all these features will be corresponding to a new column in your data matrix. And for each house you have in your data set will be represented as a new row in your data matrix. So your first house, on the market, you have so many bedrooms and it's so many square feet and whatnot. And then it's equal to, $1.5 million because it's in San Francisco. And, second row, you have another house. And, and then you solve the mx equals y equation. It's an optimization problem. You solve the best x that minimizes the error. And then you will have test cases which you have certain features but you don't have the price, so you'll have to predict the price by substituting x into your equation and taking out the right hand side vector, which will be corresponding to your predicted price.
Awesome. That's a great example. Yeah.
Okay, good. Let me move on. So in optimization problems, in machine learning problems, we will always be dealing with, so in the heart of the problem, we will have a big loss function. That's a function of all the features of that describes the problem. In an ordinary linear square problem, you have only one feature. And, in general linear square, you could have n many features. And this loss function will be a function of all those n many features. And here, for ease of illustration, it's just chosen to be a one-featured loss function, one-feature problem. So you're just going to have one single line on the page. And if you have two features, it's going to be a surface, a parametric surface in three-dimensional space. And usually we have many, many features in interesting machine learning problems. So it's not going to be easy to plot it. So what we are trying to do in optimization is we are trying to find the global minimum of our loss function. And we don't know the whole extent of our loss function. It's too costly, or actually it's impossible to look at every single value of the loss function within the possible intervals of your feature set. Here, for illustrative purposes, here's a loss function, and here's actually the global minimum on the left hand side of the equation of the graph. Sorry, and here it says there's a local minimum, but it's quite close to the global minimum, so you could just accept that as a halting point in your minimization algorithm. And here is another local minimum. Your algorithm, the gradient descent algorithm, which minimizes the loss function, can get stuck in this local minimum. But you should be wary of every convergence you have in your gradient descent minimization algorithm, because it never really guarantees that the converged values will describe a global minimum of your loss function. But there are many things you can do to understand how your loss function behaves, and I will talk about that momentarily. Gradient descent is the typical algorithm we use in machine learning optimization problems. Here's a very simple loss function, which is basically equal to x squared. Is it? Or some, yes, half. 1 is 0.5x squared, basically. And the minimum, the minimum happens at x equals 0. And the minimum is also given by, the minimum point is also given by where the function gradient equals to 0. In one-dimensional, loss functions with only one feature, is in this plot. The gradient is basically equal to the first differential of f with respect to x, and we are solving for the first differential of f with respect to x equals to 0. This corresponds to the minimum point where the loss function attains a global minimum. And in this, I will talk about some different optimum points, like minimum, maximum, and saddle points in a moment. For the converged value of your gradient descent algorithm, for it to signal a local minimum, at least, the second derivative of your function, of your loss function, must be positive in the vicinity of your solution, x equals x0, where f is equal to 0. And in the gradient descent algorithm, we have an iterative update formula. So at each step, we we compute the gradient of the loss function, and then that gives us, how fast, or that gives us the rate of the change of the loss function with respect to the input variable. And if it's, we are trying to find the value of x where the loss function attains a minimum. So we have to move towards where the gradient of f becomes, it points in a negative direction. If here on the right-hand side of the x square function, if the gradient is all positive, and if we start from here, we are trying to find the minimum value. We calculate the derivative of the loss function, and it's going to be a positive, number, and then that should signal us to make a step in the negative direction. Hence, there's a negative sign right here on the update formula.
What is an example where gradient descent would be applied when you're doing machine learning or deep learning?
Gradient descent is an optimization algorithm. In pretty much every machine learning algorithm, we have a loss function where we're interested in finding the argmin of. So the input features, which gives the minimum possible loss function, is also the solution to your machine learning problem.
Awesome.
So the book talks about the 3 typical critical points that could be encountered. These are all local or global optimums where df dx equals to 0. So let's say we ended up at this point at the end of our optimization algorithm. In order to see if it's a minimum or a maximum, you just need to look at the second derivative, and you have to look at the second derivative in the vicinity of your solution. And if the second derivative is positive, it signals a positive curvature of the loss function. So in any direction you move from, your x equals x0, the solution point, if the second derivative of your loss function is 0 in that vicinity, you will always, in any direction you make a step, you will always find loss function increasing. So this is a good, converged state of your loss function. You have found the minimum. Congratulations. And in a gradient descent, you would probably not end up in a maximum, because gradient descent always goes downhill. But if you happen to have that, or if you're doing a gradient ascent algorithm, if you're instead of minimizing, if you're maximizing your loss function, where the solution x equals x0 solves the optimization problem you have. In the vicinity of that solution point, if the second derivative of your function is negative, that means the loss function is has a negative curvature, which means, you know, in any direction you make a step and moving away from this, the solution point, the loss function will be smaller than at x equals x0. And here's an interesting critical point called saddle point. The saddle point actually happens very rarely because gradient ascent algorithm kind of moves in a random fashion in your solution space. Saddle point is defined by in your solution point where the first derivative of f is equal to 0 at, you know, called x equals x0. If the second derivative is positive and negative at different directions in your loss function, then it's a saddle point. And this can be extended to multiple dimensions as well. Say if you're in a 100-dimensional space and your loss function has 100 inputs, and you have found a point in that 100-dimensional solution space where your loss function, the first derivative of your loss function with respect to every input variable from xi, from x1 to x100 is equal to 0. That means it's an optimum point, it's a critical point. However, if one of the second derivatives of f with respect to one of the 100 feature vectors is negative and the rest of them are all positive, that means it's a saddle point. It's not a local minimum or maximum.
Awesome.
This is a better illustration of a saddle point in 2 dimensions, in 2-dimensional solution space. And in a second now, I'll be talking about eigenvalues and eigenvectors again. So here, your function, I didn't put the function here, but it should be x1 squared minus x2 squared. This plot is from the book. And at x1 and x2 equal to 0, this point, we have a saddle point. It's a critical point where the first derivative of f with respect to x1 is equal to the first derivative of f with respect to x2, which is equal to 0. And the second derivative of f with respect to x1 is its curvature at this point in the x1 direction. So if you're just moving in x1 direction like this, you're moving on this blue isoline. It's all negative. It's like it looks like a negative x squared if you look at it from this direction. And if you look at it from this direction, if you're looking at f varying with respect to x1, the second derivative of f with respect to x1 is positive. I think I have made a mistake here. It's a typo. Is it? Yeah, I think this should be positive, this should be negative. So I should correct that. This is f of x1, right? Like this. And the second derivative is positive because the curvature is pointing upwards. So this is how a saddle point looks in a 2-dimensional input space, solution space. And the book talks about Jacobian and Hessian matrices after this point. This slide, I'm just looking at it right now, but I think it's kind of out of order. Let me see. Just bear with me.
No problem. Thank you for putting this together.
Okay. Let me talk about the Jacobian matrix first. So the Jacobian matrix is mentioned very briefly in the book. However, I have done a lot of work with system of equations while I was in grad school, so I'm fairly well acquainted with Jacobian matrices. Jacobian matrices come into play when you have a system of equations, when your function of f takes in a n-dimensional vector or n many scalars and spits out another n-dimensional vector. So it basically characterizes a set of simultaneous equations where each equation is like set like this. If this is a linear equation, then you're in luck, because you can describe your solution by x equals b, and all the tools are available to you to look into the characteristic equation of A, and there are many. If A is very big, it's a very large matrix, then you could harbor in some iterative methods to solve this equation. But however, if the system of equations, you still have a system of equations, but if the equations are nonlinear, then you can't solve ax equals b. You don't even have an ax equals b, because each of these f has nonlinear terms like x1 squared, x2 times x5, and whatnot. Newton's method in this problem helps us solve for f of x equals 0. It's a root finding problem. For here I have described Newton's method for the one-dimensional case, which is you have f of x squared minus 5 or something, and you're trying to solve for the equation f of x equals 0. Newton's method, geometrically, it starts with an initial guess, and then makes its way towards the root by making incremental steps. The step size given as a function of the derivative of f with respect to x. So if your function is ascending, which means the first derivative of your function is positive, you should be moving backwards. So this is for one-dimensional case. For multi-dimensional case, the solution for f of x equals 0, instead of first differential of f with respect to x, you have a matrix of all these functions with respect to all the inputs, which is going to be an n by n matrix. It's going to be a symmetric matrix as well, because the f1 of x2, the fi del xj is by definition equal to del fj del xi. So for multidimensional cases, you will have a matrix that gives the differentials of the functions with respect to the input variables, and your step size will be given by the inverse of Jacobian dot into the f vector. So this is a root finding problem, but in machine learning we don't deal with root finding problems. However, we minimize a loss function. However, it's actually if you just take the first differential of this function, you can have like df dx equals 0, which is going to make it an optimization problem, which is going to be relevant to our machine learning problems. So if we take the first differential, of both sides, And then that first differential will propagate into our solution scheme, into our iterative scheme. And this Jacobian will be differentiated again. And then you'll have a second order differential matrix. So the Hessian matrix is given by this equation, the second differential of your loss function with respect to any two input vectors. It's relevant for functions where it maps a vector to a scalar, just like our machine learning loss functions do. So the Newton's method, I kind of explained this verbally. The Newton's method for optimization boils down to this equation. Instead of Jacobian, we have the Hessian matrices. But the book also talks about, let me see what the next slide is. Let me look at my notes. So the Hessian of the loss function gives us a lot of information about how the loss function behaves. Whether it has saddle points or minimum points. It's not easy to calculate the Hessian matrix for every input of the solution space, but for critical points, when we reach a converged point, a solution point, we can evaluate the Hessian matrix to see the behavior of the loss function in the vicinity of the solution. So the second order Taylor series is given by this approximate formula. You might be acquainted with this Taylor series for a scalar function, and here the book gives the Taylor series for a vector input, and I've written it out here. You take the first three terms. The first term is the zeroth order term, and the linear term is the second order term, and you truncate the third order term, so it's a third order accurate approximation to f of x, to your loss function in the vicinity of x0, which is supposedly your solution point or your mid step in your calculations in your iterative scheme. And if you're using a second order optimization scheme using the Hessian matrix, then here the epsilon of your step size, I think this is straight from the book as well. I rewrote one of the equations in the formula in the book. The book uses a slightly different notation. It uses G for this whole gradient f of x0. Here, the equation gives you an approximation of your loss function, epsilon step away from your initial point x0. And I don't know if I really need to get into too many details, but the book also explains an optimum step size for your second order solution scheme using a Hessian matrix. And it ties it to the eigenvalues and eigenvectors again. Let me see what I was going to talk about in this slide. Oh, so the Hessian matrix. Okay, so this is actually one of my favorite parts of this concept. So the Hessian matrix gives you very valuable information about the loss function, and the Hessian matrix is by definition a symmetric matrix, and the eigenvalues and eigenvectors of the Hessian matrix will give you the maximum curvature at a given point x0. And in the saddle point, for instance, the eigenvector will be in this direction and in this direction. It's going to have two eigenvectors. It's going to be a 2 by 2 symmetric matrix, Hessian matrix, that is. And in the vicinity of this critical point, H is going to be come out to be a negative semi-definite matrix, which we don't really like, because it looks like a critical point, looks like a solution to your optimization algorithm, but actually it's just a saddle point. So for this x0 point right here, I point out with the red dot, xthx will come out 0. And one other thing is the eigenvalues that correspond to the eigen directions, to the eigenvectors, gives you the curvature at that point, which is really nice. It's already included in this characteristic equation of the Hessian matrix. So I have a couple more slides. And so the gradient descent in our optimization algorithm, if the Hessian matrix has, if the conditioning number of the Hessian matrix, I talked about the condition number being equal to the ratio of the maximum and minimum eigenvalues. If this condition number rather, is large, then you might run into some problems in your gradient descent algorithm. The condition number large means the eigenvalues vary greatly in terms of magnitude. The eigen vectors, put the eigenvectors and eigenvalues of the Hessian matrix at this point, the Hessian matrix of the loss function at the solution point, which is 0, 0 for this function. Here you're cutting through the iso lines. They are like more closely packed here in this direction, which is the maximum eigenvalue direction, the eigenvector direction, which corresponds to the maximum eigenvalue. And here it's the variation is a lot more slow in the minimum eigenvector direction. And in your gradient descent algorithm, if you start your gradient descent algorithm at a random point like in here, the gradient of the loss function will point you in this direction. So you'll take a step size in that direction, but the component of that direction, the Vmax, the maximum eigenvector component of this direction, will bounce you from side to side, because your loss function is changing very rapidly in that component of your step. So this is just an illustration of a poorly conditioned loss function, a poorly conditioned Hessian matrix of a loss function. And that's why it's very important to normalize your loss function, normalize your input variables, and calculate your loss function based on the normalized input variables.
Where would you see an example of this in practice?
In practice, we can again look at the simple predicting the house values problem with two continuous input variables. One could be the I mean, let's look at the total, or maybe we could look at the total area could be one continuous variable, and what another thing could be a continuous variable. Maybe it's distance from the center of the city or something. So it's like, one is an area, the other is a distance. They're in different units, and one could reach thousands of miles, or maybe, I don't know, maybe thousands of square feet or hundreds of square feet. And the distance from the center of the city could reach only several miles. So you're trying to butt against two random variables, two input variables rather. One is in the range of 0 to maybe 10 miles. The other is in the range of, I don't know, like some on the order of hundreds of square feet. And since they operate in different dimensions and different ranges, the loss function calculated based on those two input variables will give you a loss function kind of looking like this, I would guess. In one dimension, the loss function will vary very rapidly. Like if you're going from the center, if the house from the center of the city is, from 5 miles to, I don't know, 10 miles, that's a difference from 5 to 10, might have a great effect on the price of the house. And however, the house, the land area the house sits on might not have such a great effect on the house price. And maybe this dimension will be the house area, and this dimension will be the distance of the house from the city center. And I think that's all I'm going to say about the Jacobian and Hessian matrices. And the very last section of the book talks about optimization with some constraints. I didn't prepare too many slides for this. I just have this one. And honestly, I don't want to get into too many details of this. In machine learning problems, I don't really remember coming across machine learning problem with a certain constraint. Although I think I can maybe probably think of something. But to cover all aspects of a general optimization problem, I can say a couple of words about an optimization problem with constraints. There's this thing called Lagrangian multipliers. So if you have a function f of x that is your loss function that you're minimizing, you're trying to find the x that minimizes this loss function. But your x could be subject to a particular set of constraints. Like you might want the vector x to have a unit norm, or a certain part of x, like certain feature in x, to be in a certain range. Like you want the minimum of this loss function f of x. You want to find the x that minimizes the f function, for which the second variable in x is permitted to be only within 3 and 5 or something. In which case, Lagrangian multipliers come to your rescue. You have two terms here. One is called an equality term. The other is an inequality term. I've never done any work with the inequality part, but I have done some work with the equality part, equality constraint. And the whole function with the constraints is actually, it boils down to minimizing this whole function, with 2 or 3 terms in total, instead of just the f of x that you need to minimize, ignoring the constraints. So in the end, instead of running your gradient descent on f of x, you run your gradient descent on the additional 2 terms, which add to your loss function. So this whole thing becomes the function that you're minimizing, you're optimizing on. And you can run your gradient descent and whatever algorithm you have for optimization on this summation. I think this is all I'm gonna say about the constraints, and that pretty much concludes my presentation.
Wonderful. Thank you so much, Shafak. So the chat room's been pretty quiet so far. I think people were pretty into your presentation.
Oh, yeah?
Yeah.
I might have made some mistakes here and there. I had some typos. I just, realized while I was going through the slides right now.
That's okay. So we want to kind of open it up for these guys in case, we do have a few minutes left, for our normal hour session. But if there are any questions from the audience, we welcome you guys to put it in the chat, and we're happy to pose those so that people can ask. And
okay.
Yeah, let's
Well,
see.
I will give this presentation again in class.
Yes, that's correct.
It's going to be 2 weeks on Monday, I think.
Yeah, so on Monday, actually, I think it's this upcoming Monday. Let's double check that for everyone. So for those that are just joining us too, we also run these sessions in person in San Francisco on every other Monday. And so the next one is taking place this Monday, February 27th, and that's at Sandbox Suites at 6:30 p.m. So if you prefer learning in person and you want to kind of dive more in there, you're welcome to join us as well. We also host alternatively in-person sessions each week on deep learning on Thursdays, and in that we cover different lecture series. So the last lecture series that we covered was CS231N from Stanford on computer vision, and the one we have just started is the new deep reinforcement learning from Berkeley, and I forget the number for that associated with that one, but I can look it up. Oh, there is a quick question right here in the chat. So it says, the condition number is very intuitive for me. Is there something you can add to its definition?
Oh, I think I have talked about the condition number as much as I could. But, in person, I would like to have this as a, two-way discussion rather than, like a lecture.
Great, yes.
Because I just, read through the book, earlier this week, and put up the slides like yesterday and this morning a little bit. And I like the presentation style a lot, but I really want to have like a whiteboard and draw things on there too.
Definitely. So in the in-person sessions, we do have whiteboards available, so we can do that as well. Are there any other questions maybe from the chat, or do you think there's anything else you could cover about the condition number? Maybe.
Sure, I can go through it again. Sure. So the condition number is actually, it is not defined by this, not defined by this. It's defined by this. This is the condition number. The ratio of relative error in X to the relative error in B. So you have this system of equations AX equals B. And you put in an unknown, you're going to solve for that. And B here. And, depending on your problem, B could be something that you're measuring. Like it could be some velocity or something. And you have an equipment, a laser equipment or something. And then or it could be, I don't know, it could be like maybe in Hadron Collider or something. You could have, some problems and you're measuring the velocity of some particle, and B is there and you're measuring it with very expensive equipment, but they are never perfect. And this B will never give you the exact picture. So it will have some kind of error in it, because it's an experiment. It's the nature of experimentation. And you want to know how this error is going to propagate to your unknown vector. You are curious about this one. You're trying to solve for x, right? This is what you care about.
Right.
You know A, and you can measure B. And from the knowledge of A, you want to have a prediction of the magnitude of the error that's going to come out in x. So for the perfect case, you have ax equals b, and x is the solution to b. But b, you will never be able to get b is with 100% accuracy. You will always have this epsilon. And how is this epsilon going to transfer into your unknown solution vector? This is what you care about, and you want to have an estimate of this error that's going to get into your unknown vector. And I can do this in class. It's a couple lines of derivation, but here the condition number is defined by this thing, u divided by x, which is the error, the ratio of error with respect to the solution vector. These are all L2 norms, so it's a measure of the magnitude of your solution vector. And this is, I should have put an epsilon here, not an e, which is the error, the ratio of the error to your right-hand side vector. And this, again, boils down to how well you know the characteristic equation of your coefficient matrix A. And the condition number gives you the worst case of this error propagating into your solution vector. So the worst case happens. So this is kind of like an upper bound of the error you will experience in your solution vector. The worst case happens under this condition. If epsilon error perfectly aligns with the eigen vector that corresponds to the minimum eigen value, and if b corresponds to the maximum eigenvector, I should say. And here b and epsilon are actually orthogonal to each other, because I mean, you can't really say that for every case, but assume A is semi-posidefinite and it's real numbered and a symmetric square matrix, then B and epsilon, in this case, they're going to be orthogonal. And actually, if you have seen the Stanford, if you followed along the Andrej Karpathy image recognition class, CS231N, he mentioned this in one of the lectures. He didn't talk about the condition number, but he talked about the image. Like, he has a cat image, and then he's running his deep learning algorithm to find the probabilities of that cat image with respect to his categories. And he can find, he said, some random noise that is in a perfect orthogonal direction in that very high dimensional image space, image pixel space.
Mm-hmm. That
is a very, very small vector. But without that vector, that epsilon vector, your probability of that cat image being a cat is predicted by like 99% or something. So your deep learning algorithm works really well. But if you introduce a very clever white noise error over that image, the image is going to look pretty much the same to you with your naked eye. But there'll be a very small error in there that's going to shoot the right-hand side vector off to a very dangerous direction. And your x vector will, initially your deep learning algorithm had predicted the image to be a cat by 99%. But with that little epsilon smart, ingenious error, that it probably drops down to like something like 60%, and the cat image still looks pretty much same to you. And he talked about the little manifolds in the solution space, and and he said, like, this is really unnerving, and there's no solution to that really. So this is all about the error propagating into your the left-hand side of your equation into your solution vector.
Wonderful, thank you.
Mm-hmm.
And there was one more quick question.
Surely.
Looks like they asked if you can give a little bit more intuition regarding Hessian and eigenvectors again, if you don't mind. So maybe how specifically they would relate to deep learning, or how to think about them when you're doing a deep learning problem.
The Hessian and eigenvector. So that's two different topics.
Yes.
Eigenvector, it took many, many years to really get a good grasp of it. Eigenvectors come out in like any discrete problem. It could be a graph problem, like the page rank in Google algorithm is actually, it corresponds to the eigenvalue of the maximum eigenvector in a particular matrix that defines your adjacency matrix in a graph, in a social network, for instance. So eigenvectors come out there as well. And eigenvectors are also embedded in differential equations that will give you a certain solution space. And it's in fluid mechanics, it's in solid mechanics, elasticity and everything. So it is a mind-boggling concept. But if you look at the ax equals b equation, everything comes from there, from ax equals b right here. And basically, it's going to be a little loose concept that I'm going to offer. Looking at ax equals b, we're looking at this problem from where we stand, from a Euclidean space. But the matrix A, he has an intrinsic language, like its own mother tongue, and that's its own coordinate system. So your Euclidean system is like x goes in the horizontal direction and y goes in the vertical direction and z goes out of the page, comes out towards you, and they are all 90 degrees away from one another, all orthogonal to each other. But the matrix A has a particular intrinsic coordinate system. An eigenvalue decomposition comes from singular value decomposition, and singular value decomposition comes from explaining the variance. And there, things get tied to statistics and machine learning when you talk about explaining variance. So just without any ability to draw some functions and lines and plots, it's not too easy for me to be very clear. But think of eigenvectors as an intrinsic coordinate system that explains the linear transformation that's defined by the matrix A, and these eigenvectors and eigenvalues mean different things under different for different problems. When you're looking at the Hessian matrix, the eigenvalue and eigenvector will give you the direction where the curvature reaches a minimum or a maximum. Incrementally, actually, it's a maximum. It reaches a maximum, but incrementally. First, like here, the Hessian matrix of this loss function. The loss function has two inputs, right? x1 and x2. So Hessian matrix can be constructed with respect to those two, the second partial derivatives with respect to those two input vectors. And the Hessian matrix will have it's going to be a different matrix at every single point on the surface. So you don't have only one Hessian matrix. You have only one Hessian matrix for a given point, x1, x2. So we're looking at the saddle point. That's the point of interest. We're looking at the Hessian matrix at this point. And the Hessian matrix, if you look at the eigenvectors and eigenvalues of the Hessian matrix, it's going to give you the variation, the maximum variation. So the largest eigenvalue will give you the largest variation in this on this curve. Largest second differential variation, rather. Jacobian will give you another information. Hessian is about second derivatives, is about curvature. So the largest eigenvector will point in the direction where the directional derivative will give you a maximum at that point of interest. And that's your first eigenvalue and first eigenvector. And once you found that, you take that information out of your function. So you forget about this x2 direction, and you have only, you collapse everything in, one less dimensions. In this case, it's going to be one dimension left. And then in this one-dimensional space, you just have one dimension to choose from anyways, but you can extrapolate this to multiple dimensions. You can look at a Hessian matrix of 10-dimensional, loss function, and the maximum eigenvector will give you the maximum direction, the direction where the maximum curvature happens. And the second eigenvector will give you, the second biggest eigenvector will give you the second largest direction to attain the maximum curvature. So at each, so you calculate the eigenvectors and you sort them from descending from the largest to the smallest, eigenvalues, and each eigenvector will give you the incrementally decreasing maximum curvature directions. I think this is all I can explain just on voice right now.
No, that's perfect. Thank you so much, Shafak.
Okay, I hope it was of some help to some people at least.
I think so, definitely. Okay, great. So it doesn't seem like we have any other questions in the chat room. Sometimes it's like a minute or two behind. Yeah, we have someone that said, good explanation. That's awesome. And we had someone else that also gave input. They said, think of Hessian as a matrix of second derivatives. So you did go over that, which is great. So yeah, we do really appreciate your time and going through these presentations for us. And so we're going to just remind people again that what this is kind of a community learning experience. We are covering the deep learning book together as a group. We do encourage you to read the chapters on your own. Obviously, you'll get the most information out of that. But we do have a volunteer present on each chapter every week. So if you can join our meetup page, if you would like to volunteer, you just go onto the Excel spreadsheet. There are two tabs at the bottom of the spreadsheet, one that has online and one that has San Francisco. So obviously, if you're not in the area, we would ask that you would volunteer for the online portion. If you are in San Francisco, would like to volunteer for that one, we would appreciate that as well. And then the presentations can be as short as 10 minutes, but as long as an hour or two, maximum probably 2 hours. Just to give people a nice overview of what was covered, and then also to just make sure that if people have questions or didn't quite understand something, that someone can try to help with that as well. So we do thank you very much for your time. And Shafak, do you want to share your personal information with anyone, maybe your LinkedIn or your email, in case people have questions or want to follow up with you?
Surely. So I was just typing up a comment on the YouTube chat, thread.
Yes.
I put the presentation PDF file, and I could. Let me see. It didn't.
Oh well, actually, I posted at the beginning of the chat. So it's already in the chat, and I also posted it on the meetup page. So okay. People should have access to it. Yes.
Sure, and. I'll be around. I'm following the reinforcement learning if people are also would like to join that.
Definitely. You mentioned that you're also looking for full-time work. So if you wanted to share your information in case anyone wants to reach out with you, that might be a great idea too.
Oh, sure.
Yeah.
Yeah. How can I do that? Post it on.
Yeah, post on the meetup, or just send it to me and I can post it for everyone. We can share your LinkedIn and your email if you're comfortable with that. Yeah.
Sure. Yes. I can send you momentarily.
Okay, perfect. Well, then that's it for this week, guys. We do really appreciate you joining us. I'll go ahead and share Shafaq's information in case you want to reach out to him or have any follow-up questions. And of course, we encourage you to be involved and tune in and subscribe to our channel so that we can continue posting these for you and you can follow along. So thank you very much, and I hope you enjoy the rest of your weekend, and thank you for learning with us.
All right, thank you very much.
Bye.
Bye-bye.